Welcome to the final part of Chapter 12. In this section, or in this video, we're going to address equilibria and solubility and equilibrium with acids and bases. We'll wrap up with a short discussion on Gibbs free energy and equilibria. So we're going to start off thinking about something called the solubility product and molar solubility. So we talked about solubility earlier in the semester as kind of a black and white soluble or not soluble. But even the most soluble salt has a saturation point, and an insoluble salt has even if it's just a minute or negligible amount, does have an amount of solubility, which is why something like the insoluble salt limestone does over many years erode, right? Because if you keep washing that water away, if there is an equilibrium of solubility, you are eventually over time going to lose that salt will dissolve. And so we can write an equilibrium expression for solubility. For instance, if we're looking at calcium hydroxide here, we can write a solubility reaction, right? That's going to be calcium hydroxide as a solid in equilibrium, if you put it in water, with aqueous calcium ions and 2 aqueous hydroxide ions. This would be our solubility reaction. If we wanted to write an equilibrium expression, we absolutely could. The equilibrium constant for a solubility reaction is identified as KSP, or is sometimes called the solubility product. And because we leave solids and liquids out of solubility expressions, it's just K equals the concentration of calcium ions times the concentration of hydroxide ions squared. The molar solubility, and so even though it is not particularly soluble, you see K is 7.9 times 10 to the negative 6. Very, very small number, means that the starting materials are favored, right? So this reaction, equilibrium lies far in the direction of the starting materials, but there is a small amount that is dissolved, right? And that does allow us to compare solubilities, right? These are all fairly insoluble salts right here, but you can actually compare one to the other, right? Let's see if we expand that a little bit for my old eyes. All right, silver phosphate here is going to be considerably less soluble than silver carbonate. Both are relatively insoluble, but there are degrees. Okay, so molar solubility is the concentration that is dissolved at saturation. So it's once you've reached equilibrium, as much of the salt is dissolved as is possible, and it is going to be this kind of dynamic equilibrium like we saw, with water liquid going to water gas. Molar solubilities can easily be determined using some KSP values. So I'm going to show you how to do that here using an ice table. So we're going to take a look at calcium phosphate, and we're going to determine the molar solubility. So I think just for the ease of you watching this, I'm going to add a page. You could certainly solve this problem at the bottom of your notes, but I'm going to go ahead and use this blank piece. So I skipped 1210. That one's worked out in your book. You could certainly use that one for practice with calcium fluoride, but we're going to look at calcium phosphate. So calcium phosphate is Ca3PO4 right? Because calcium is a +2, phosphate is a -3. And we're starting off with the solid salt. So we're going to write our reaction. That's going to leave us with 3 calcium 2 plus aqueous ions, and 2 phosphate, 3 minus aqueous ions. We can write our equilibrium expression. It's going to be calcium to the third times phosphate, PO4, 3 minus, squared. Now, because I do want to make my ice table, I'm going to go, oh, well, maybe not do that. Let's put that back. I am going to move this down. I want to make my ice table right underneath here. So, initial change, equilibrium. So, initially, we have, solid calcium phosphate, and it's solid the whole time, so its concentration doesn't change. And it's not in the equilibrium expression, right, for that reason. But at the very beginning, before any of it is dissolved, there is 0 calcium and 0 phosphate ions in solution. So the change is going to be, we're going to be able to get a stoichiometric ratio. For every 3 calcium ions, we're going to have 2 phosphate ions. All right, so I'm going to add 3x and 2x. You're going to use those stoichiometric coefficients here. So I know my equilibrium concentrations are going to be 3 times x for calcium, 2 times x for phosphorus. Okay, so we're going to solve for KSP here. This solubility, we're going to solve for the molar solubility by filling in. We know that KSP is 2.0 times 10 to the negative 33. We're going to fill in our equilibrium concentrations. We have 3x cubed times 2x squared. And so let's simplify that a little bit. We're going to have 2.0 times 10 to the negative 33 equals 108x to the 5th. Don't forget to distribute that number, right? Take 3 to the 3rd times 2 squared. Then when you're going to solve for that, you're going to divide by 108, right? You're going to take everything to the, to the 5th root, or you can raise it to the 1 over the 5th power, and you're going to get x. And what's nice about this is x is actually your answer. Now, if the question asks what is the concentration of the calcium ions, you can figure that out by multiplying it by 3. But this right here is your molar solubility. This lets you know how many moles of calcium phosphate are dissolved. So you actually can stop right here and you have answered this problem. Right? And so you can see this worked out on this slide here. We are actually going to skip the common ion effect, and we're going to move straight into acid-base equilibrium, so you do not need to focus on the common ion effect for me. All right, getting into acid bases and using equilibrium to solve problems is important, but we need to cover some definitions about acids and bases. So there's 2 definitions that you should know, Arrhenius and Bronsted-Lowry. Bronsted-Lowry doesn't go against Arrhenius, but it does expand our knowledge of acids and bases. Arrhenius acids react with water to form H+, but I'd like you to write in here also H3O+. H+ often reacts with water, and you wind up getting H3O+, so it's good to know that those are often spoken about interchangeably. An Arrhenius base gives hydroxide. A Bronsted-Lowry acid is a proton donor, right? It gives away a proton in H. Bronsted-Lowry accepts the H, accepts the proton. All right, so those are some definitions that you are responsible for. We've talked about weak versus strong when we talked about solubility and electrolytes. A strong acid, and these are the strong acids that you are supposed to already know. I think this one might be new. I won't throw that one in. to trick you, but you should know the 6 that I've asked you to memorize already. A strong acid, when it reacts with water, so we'll take that first one, HBr. When it reacts with water, and HBr, I think it's a gas. It might be a liquid. We're going to leave that out. We're not going to worry too much about that right now. Is going to completely react to give us H3O plus. Notice the HBr gives up its proton. The water accepts it. It's acting as the base. And Br minus. Actually, I'm going to skip to strong bases really quickly. A strong base is completely dissociating, or essentially completely dissociating, and becomes completely protonated. So oftentimes when we think about a strong base, we are looking at something like, let me flip to my note here to give you the example that I had planned. If we think about something like sodium hydroxide, well, we know that this is completely soluble. So we're going to leave out the spectator ion here. OH minus is frequently our strong base, and it's in solution, and it reacts with water. And now water is actually going to act as our acid, and the hydroxide is going to take that proton away from the water and produce OH minus. So you wind up with OH minus on both sides. The way that is typically written, and it might be less confusing, is if we have this base and we have any acid around, anything that's willing to give up that proton, they are going to react to form water. All right. We're not going to have to deal with this too much, but strong bases are going to completely react to form water. Now for what's going to be more interesting from an equilibrium standpoint, weak acids and weak bases. So if we take a look at a weak acid, something like HCN. HCN in solution with water is going to partially react, and you're still going to have plenty of starting material. HCN is the acid, so it is going to donate the proton. So we're going to wind up with Cn minus. And then water is going to act as the base, and it is going to accept that proton, and we're going to get H3O plus in solution. All right, so that would be the equilibrium expression for HCN in water. A weak base, something like ammonia in solution, is going to accept a proton. So water is going to act as our acid here. You're going to see this note, it's a little bit further down, but water acting as both an acid or a base means it's amphiprotic. So the NH3 accepts an extra proton and becomes positively charged. And the water gives up a proton, so we've essentially made OH in solution, right? So it's also an Arrhenius base. Okay, so that's how you would write those equilibrium expressions. Now, a little bit of vocabulary here, right? We just talked about amphoteric. Conjugate acid-base pairs. So it's especially important when we're looking at an equilibrium because the reverse reaction is also occurring because it's dynamic, that you're always going to have something called a conjugate acid-base pair. So if we take a look at, say, I'm going to jump back up here. We know that HCN is our acid and that water is acting as our base. Well, a conjugate acid is formed when the base accepts a proton. So if H2O is our base and it accepts a proton, this is called our conjugate acid, right? Because in the reverse reaction, it's acting as the acid. HCN donates a proton, and so the Cn minus is the conjugate base, right? In the reverse reaction, it is accepting a proton, it's acting as a base. If we did the same thing here for our ammonia example, ammonia is our base, and NH4 plus would be our conjugate acid. H2O is acting as the acid, so OH minus must be the conjugate base. All right, you should be able to identify those pairs. We can write equilibrium expressions for these. And so, for instance, let's say we're looking, and I'm just going to use kind of this random space we have here. If we're looking at a general expression of an acid, HA plus H2O, in equilibrium with A minus, the conjugate base, and H3O plus, the conjugate acid, we can write an equilibrium expression called Ka. And something to note is that water is always a liquid, so it's never actually in the expression. We can do H3O plus times A minus, all divided by HA. It's conjugate acid-base practice. We actually will come back to an acetic acid problem in a little bit. All right, but there it is, Ka. This is called, all of these specific Ks, equilibrium constants, of course, have special names. So like KSP with solubility product, Ka is the acid ionization constant. And why is that important? Well, Kas can give you information about strength, right? Ka is the ionization constant, and the larger the Ka, the stronger the acid. So it's not a strong acid, but you could see here, for instance, that hydrofluoric acid is considerably stronger than hydrocyanic or HCN. That 10 to the minus 4 versus 10 to the minus 10, right? So this one's much bigger in comparison. You can also do the same thing for bases and get Kb. You can do Hb times OH minus over B, and that's going to give you the base ionization constant, Kb. You most frequently deal with Ka. There are ways to get Kb from Ka, so most tabulated data is going to give you the acid dissociation constant. Before we jump into solving problems with Ka, I want to make sure that we understand pH. pH is a way to measure the acidity or basicity of an aqueous solution. It measures, when we talk about pH, it is a measure of hydronium, H plus or H3O plus. There's also something called pOH, where you measure the hydroxide concentration. What is more common to need to know is pH in its general scale. You do need to know what pOH is, and we'll look at that. But this scale is from 0 to 14, and 7 is neutral. Anything below 7 is acidic. Anything above 7 is basic, meaning the balance of H3O plus to OH minus leans, either acid or base. Now, pOH has the opposite trend because you're either looking at the hydronium concentration or you're looking at the hydroxide concentration. And if you don't already know, P of anything, right, means it's a log function. So P of X would be negative log of whatever X is. So pH is negative log of your hydronium concentration. Right, you see that right here on the slides. pOH would be negative log of the concentration of hydroxide. All right, so relatively simple equation here. Oh, and of course, it's on the next page. And px, pH, POH. And if you have one, you can always find the other. This is something important to know. POH and pH together always equal 14. So if you know one, you can easily find the other. And usually you're going to be, if you're asked about pH, you might have to go through POH. And let's do a couple of examples to highlight how easy this can be. All right, so these first two examples are using strong acids and strong bases. And they essentially completely dissociate, so we don't have to worry about equilibrium. So I want to know what is the pH and POH of a 0.2 molar HNO3 solution. So if, maybe I'll use a pencil. Here we go. HNO3 is going to completely dissociate into H plus and NO3 minus. And since this is 1 to 1, if there is 1 mole of HNO3, there would be 1 mole of H plus. If there is 0.2 moles HNO3, there will be 0.2 moles H plus. So pH is pretty easy. It's going to be negative log of 0.2. So the pH equals 0.699. Well below 7, makes sense. It's acidic. If I wanted to find the POH, I need to just do 14 minus 0.699. And the POH is 13.301. All right, so you always want to make sure that you're answering the question that's being asked. And we were asked for both pH and POH. Now let's do one with a strong base. We know that NaOH in water is going to completely dissolve. So I'm just going to do the solubility here, reaction. We know it's going to completely dissolve into Na plus and OH minus. So if I have 0.1 molar NaOH and there's 1 hydroxide per each NaOH, I'm going to have 0.1 molar hydroxide. So POH would be negative log of 0.1. And that gives us a POH of 1. It's pretty easy math here. That means that the pH is 13. Well above 7, very basic. Exactly what we'd expect of a strong base. Now, looking at what to do for weak acids and bases. We are going to use an ice table here. Now, I don't know if I left enough room here, so I am going to go ahead and give us a bit more space, and we're going to solve this problem here. It's on the slide, and you have it in front of you in your notes, so we're going to go ahead and solve that here on this blank page. So I'm using acetic acid, so I need a couple things. I need the reaction, CH3COOH. We're going to do that reaction in water. And there's a significant equilibrium that goes back to the left, but we are going to have some H3O plus, right? Water's conjugate acid, and CH3COO minus, our conjugate base. This is our balanced reaction. We also can write our Ka expression. Water is a liquid that's really important to recognize. Everything else is aqueous. And so when we fill in our Ka expression, it's going to be CH3COO minus H3O plus over CH3COOH. All right. Okay. Now for our ice table. Initially, we are told that we have a 0.1 molar solution. Our H2O liquid is going to be constant. That's not going to be part of it. And we're not going to have any hydronium or any acetate right at the beginning. The change is based on the stoichiometry. We're going to lose some amount of acetic acid. And we're going to get, because it's all 1-to-1, we're going to make that same amount of the H2O plus and the CH3COO minus. So our equilibrium concentrations will be 0.1 minus X, X, and X. Now, we know that Ka equals 1.8 times 10 to the negative 5, given to us here in the problem. So we're going to plug in our equilibrium concentrations, and we're going to make an assumption. So let's plug in first. We're going to have X times X over 0.1 minus X equals 1.8 times 10 to the negative 5th. So I'm going to give you a little kind of cheat code for weak acids. For most weak acids, and there's a test for this, but you don't have to know how to do this. Assume that 0.1 minus X is about equal to 0.1. The reason for that is because most weak acids, the equilibrium lies so far in the direction of the starting materials. And so the reverse reaction is the forward reaction is actually very small. So based on significant figures, if X is very tiny, it's still going to round to about 0.1. Now, it's important, X is important, that's how we're going to be able to calculate pH, but what we're saying is that this difference here would be negligible for the math. Don't do that for your other ice problems, but you can do that for your acid-base problems. All right, so if we assume that, then we're going to rewrite here. I'm going to go ahead and push those x's together. We're going to have x squared over 0.1 equals 1.8 times 10 to the negative 5th. Then I'm going to rearrange. I'm going to have x squared equals 1.8 times 10 to the negative 6th. X equals 1.3 times 10 to the negative 3rd. And this right here, this is what we want, right? Hydronium is X, and X is that. So I can now find pH. So I'm sorry that I didn't plan well here, but let's come over here. pH will equal negative log 1.3 times 10 to the negative 3rd. Now, this still should be acidic. It's acetic acid. It just shouldn't be strongly acidic. So it should still be somewhere below 7. And it is. It's 2.87. Right? So we did get an acidic pH, which is great. That's what we wanted. So definitely make sure you're practicing those kinds of problems. I have some extra equilibrium problems up for you on eCampus, and of course you have OWL. So that brings us to the end of those ice problems, and there's just one tiny little section that we're going to finish up with, and that is Gibbs free energy and equilibrium. Since equilibrium is that state of minimum free energy, we already kind of saw the connection when we talked about boiling points or melting points. At equilibrium, the delta G would be 0. And a chemical system tends to move spontaneously towards equilibrium. So there's a connection between equilibrium and spontaneity. So we can actually calculate delta G from our equilibrium constant or vice versa using this equation here. There is a little bit of math proving behind this, and as you read through your text, you'll get a little bit of a math story, but this is the equation that you would need. So what you would need to solve a problem like the example we're using here is you would need to know how to solve delta G. So you know that delta G of a reaction is going to be products minus reagents, right? So delta G is going to equal The sum of the products, so that's going to be 1 times, because this is a 1 here, negative 166.27 minus negative 50.75 kilojoules per mole. Again, it's just multiplied by 1. And then oxygen's already in its elemental form, so that one's just going to be 0. So delta G for this problem, for this reaction is negative 115.52 kilojoules. All right, so if we want to solve this problem, we're going to make this all just a little bit smaller so that I have some room. See the magic here. Okay. All right, so we're given the temperature. We're given the temperature. That's what we need, right? We're solving for K. So we know that if we use this equation right here, we're going to have negative 115.52 kilojoules per mole equal negative 8.3145 joules per mole Kelvin. You want to use the value of R that has joules in it because, of course, this has joules or kilojoules. So that reminds me, we need to do a little bit of manipulation here. Just move that up. There also needs to be, on one side or the other, you need to convert. So I'm just going to do it over here. I know there's 1,000 joules in 1 kilojoule. There we go. So make sure that you convert and get your units all synced up. So then we have R. Then we have to put in T. Now, if T is in Kelvin here, then we probably need to not use Celsius. So I'm going to use 298 K. LNK. And we are going to be solving for K. So we're going to rearrange this and we're going to simplify. So negative 115.52 times 1,000 divided by 0.8 divided by negative 8.315 divided by 298 equals 46.6 equals LNK. Now to finish this, you need to remember what natural log is. To rearrange this to solve for K, we're going to say that K is equal to E to the 46.6. All right, that's how you're going to finish this problem and solve. And we're going to see that K equals 1.73 times 10 to the 20th. All right, a fairly fast reaction that we're looking at there for this particular reaction. And that's it. That's 12. This is the last lecture. You're going to miss me? I'll shut up now. Please come to office hours, do practice problems, email me. I'm still here for you guys.